This is a lecture on diffusion in networks. And first we want to look at what happens in free space. We've already talked a little bit about that in terms of a random walker. And so we can have an ensemble of random walkers, and so they can do their random walks, and another one, and another one. And so what happens is that we actually get densities, right? And so you can actually create these contour plots of decreasing density, and the contour plots will actually expand outward with time. And so we know that there's a simple relationship between the diffusion length, it's the squared diffusion length, goes as 2, in this case it's two-dimensional, so it's going as 2d times the elapsed time. And so the diffusion length is actually growing as the square root of time in the case of free space diffusion. Now we can then consider what happens, sort of an equivalent case for a lattice. Okay, and so for a lattice we can think of having these nodes, and these nodes can have certain concentrations to them, and they'll have neighboring nodes, and then they'll have neighboring nodes, and these are all connected. And so this is a lattice. Okay, and if we put a concentration on one of these nodes, then in the next time, part of that will actually connect up with its neighbor. And so the neighbors will accept a certain amount of that concentration. And so we're actually not thinking of epidemics yet. I mean, so if these were individuals who were either infected or not, that's binary. But so we really do want to think in terms of continuous concentrations. And so what's happening is that the concentration is moving through the links. And so first it'll go to the nearest neighbors, and then it'll go to next nearest neighbors through these links. And since it's a lattice, I actually have links between all these. And so over time, what will happen is that the concentration in the central node will actually decrease, while the concentrations in these neighboring nodes will be increasing in time. So these will be decreasing, and these will be increasing. And if the lattice is dense and actually is a very large lattice, and if the amount transferred on each time step is actually fairly small, then the lattice is like free space diffusion. In fact, this actually would be what's called a finite difference model. And so a finite difference model is a way of taking continuous space and you make it discrete, and you can think of it as a lattice, and you can think of a concentration as being linked, or these nodes being linked to their neighbors, and the concentration is slowly diffusing away from that central node where all the concentration was put initially. And so what we want to do now is take this idea over to random networks. And so for a random network, I'll have nodes, and we'll just draw these in two-dimensional space, but you realize that there is no embedding space for a random network. And so they're just nodes and links, and there's actually no underlying dimensionality to that. And so then we can start to link these up, and so we'll just actually link up to some nearest neighbors, and maybe we'll connect up there, and we'll connect down here, and I'll actually put a connection there. Okay. And so then we can ask really the same question that we asked when we were looking at diffusion in the lattice. We can, let's say we start with all of our concentration in this node, and on the next time step, some of that will go over here, and over here, and over here to the nearest neighbors. And on the next time step, well, this guy over here actually has nowhere else to go, but can still accept concentration from that original node. But here's a second neighbor here, here's a second neighbor, and then we take the next time step, and we can now get to third nearest neighbors, and so then this guy starts to come up. And so the distances are really just measured in steps. It doesn't matter. I could have a node sitting way over here, for instance, and I can link that up, let's say, to this guy. But the point is that that's just a single step. And so if this was the original, then this would be one time step over here, and then this would be another time step over here. So not only is there no embedding dimension, but you count distances in terms of steps or links between nodes, and so it's not the physical distance on the page that you're drawing. But you could ask the question, so that if I have node A, and I'm interested in the concentration on that node as a function of time, We'd like to solve for that for a given initial condition. The initial condition might be that all the concentration is put into this initial node, or the initial condition could be some distribution of concentration, but then it'll evolve in time as things diffuse, and it'll reach equilibrium. All right, so we expect this thing to actually go over to equilibrium eventually. All right, so we want to put some math to this, and so what we'll do is we'll consider just two nodes. All right, so let's just take a node, node I, and take another node, node J, and they communicate. They have a link between them. And so what we'll do is we'll write down an equation that dci dt is equal to a incremental change. We'll call it beta. I also have to throw in the adjacency matrix because these have to be connected. These two nodes have to be connected. And then what we'll do is we'll say that the time rate of change of the concentration on I when communicating with J is actually proportional to the difference, right? So this will be Cj minus Ci. Okay? And so if the concentration on J is larger than the concentration on I, then that's positive, and we'll actually have an uptick in concentration on I. And then if this term actually is negative, then we can actually lose concentration. In other words, if Ci is actually greater than Cj, then we'll actually lose some concentration on node I. Okay. All right, so what we want to do is just looking at these two nodes. Now let's embed these two nodes in an entire matrix. And so to do that, let's bring in a summation. And so we're going to be looking still at dci dt, and it's still going to be proportional to beta. But now we're going to sum over all of the other nodes. So this is j not equal to I in the lattice, or in the network. It's not a lattice. Here's the adjacency matrix. Then we'll do Cj minus Ci. Okay, and so that gives us a discrete difference in terms of space, but it's actually continuous in time. And so we're going to be looking at continuous time solutions. All right, well, we'd like to actually still manipulate. So this equation, we could just work with this, put this in a computer, and let it run. But let's actually try to get a little bit more physical intuition on this. So what we'll do is we'll rewrite this by recognizing that when we sum over J, that Ci is actually a constant, okay, with respect to summation over J. And so this will become beta. And what I'll do is I'll bring in the sum over J, assume not equal to I, and then this will be Aij Cj, so that's just the first term. And for the second term, I can pull out the Ci, so it becomes beta Ci, and then I have the sum over J, and this will be Aij. Well, we may actually recognize that. And so in an earlier lecture, we saw that when you sum over a row or a column of the adjacency matrix, what you get is actually the degree of node I. And so that's equal to the degree of node I. So let's then rewrite this equation still in matrix form. And so what we'll want to do is use a Kronecker delta. And so just rewriting, this will become dci dt is equal to beta. Using a Kronecker, I can now have a sum over both terms, and so I'll have sum over j, and this is Aij, and here's the Kronecker delta, delta ij, and then multiplying k sub I, and this all multiplies c sub j. Now this we'll actually recognize from an earlier lecture as related to the graph Laplacian. It's actually the negative of the graph Laplacian, so this will be minus lambda ij. And so that allows us to write this equation in a very simple form. So it becomes dci dt is equal to, because the minus sign, minus beta, sum over j, the graph Laplacian, and Cj. And so then this is the final form that we wanted to get, so that it's the same as the initial form, but now it actually brings in this graph Laplacian. So the graph Laplacian has an eigenvalue spectrum, and you can look at the properties of that. You can sort of do a network spectroscopy on the graph Laplacian. And the reason why this is so important for dynamics is because I can then write an equation of free space diffusion. And free space diffusion goes as a partial dc dt is equal to minus diffusion, the Laplacian operator, times the concentration. And so we actually see that there's a direct relationship, not between that, but there's a direct relationship between the graph Laplacian and the differential operator for free space diffusion. And so in this way, we make a direct connection between the discrete and the continuous diffusion. But in the graph Laplacian is the adjacency matrix. And so we can go over to these random networks. They can be scale-free, ER, SW, and all the connectivities are actually built into the graph Laplacian. But from that point onward, what we're doing is we're really just solving a series of differential equations. And so these are they're going to be n coupled differential equations, where n's the number of nodes in the network. And we can just go over to discrete methods for differential equation solution, because this is just an ODE of n coupled variables, C sub I. So let's actually look a little bit at doing that solution. And so the solution actually does depend on the eigenvalues of the graph Laplacian. And so if we look at the eigenvalues, so EIG of the graph Laplacian, LIJ, that gives us eigenvectors. It also gives us the eigenvalues. And we know that the concentration is going to be a combination, right? So the concentration, which is actually a vector in this case, because we've got a different value on each node of the network, right? And so that actually, if I have n values, that's like an n-dimensional vector. And so then this will be equal to a combination over I of some coefficient, but then of the actual eigenvectors of the graph Laplacian. And so here we actually have the eigenvectors of the graph Laplacian. These coefficients are actually obtained by taking an inner product, right? So assuming that we have a net total concentration, the A sub I for the initial condition is actually just the inner product of VI, and I'll just write it like that, so that we recognize that that's the inner product, right? So using Einstein notation, so inner product. Okay, and so then we can just assume some initial concentration distribution across the network. That's going to be the original C sub I, and then take the inner product with the eigenvectors of the graph Laplacian. That gives us these coefficients. The total concentration then across all the nodes is just a combination over all of these eigenvectors with these coefficients. And then we plug into the diffusion equation, and there's a simple solution. And so the beauty of these solutions is that A sub I is equal to A sub I initial condition times e to the minus beta, and then here the eigenvalues of the graph Laplacian come in. That's lambda sub I times t. And so with this, we actually are solving for all the coefficients of the eigenvectors, and then we sum those up to get the actual concentration as a function of time. And so for instance, what will happen is that if we put all of our concentration on an initial node, and so let's look at concentration as a function of time. And let's look actually at log concentration, because things are decaying exponentially. But we're not going to have simple exponentials, though, because we're going to be leaking material to the neighboring nodes, and then they're going to leak to the next nearest neighbors. But there can actually also then be backlinks, and so there won't be a single exponential, but it'll actually be combinations. And so what will happen is let's take the initial node, and let's say that we start out with a concentration equal to 1. And what will happen is that this concentration will diffuse outward into the neighboring nodes. But this is log C, so this is a semi-log graph, but this won't be a straight line. Now other nodes, they'll actually come up, and some of the neighboring nodes will actually go high, but then they also will start to leak out to farther neighbors, and then those farther neighbors will gain concentration, and then it'll diffuse out to even farther. And so eventually this will actually, on a log plot, all these things will actually asymptote to equal concentration, and so these will all just asymptote to a single line at long time. And so then this will actually be equilibrium when there's equal concentrations in all of the nodes of the network. So here's a MATLAB program that does this solution, and it just solves it using just this discrete solutions with the eigenvectors and eigenvalues of the graph Laplacian. So I'm going to look at 128 nodes, and I've selected my probabilities and my m's so that I'm going to look at three different graphs or networks. It's going to be the ER, the small world, and the scale free. But they're all going to have roughly the same number or average degree. And so they're going to have an average degree of around 8. So there's going to be about 8 connections per node. So they have the same average degree, but of course you know that the degree distribution is quite different for the ER, SW, and the SF. All right, so let's look at first the ER. And so I've given it this probability of 0.06, and we'll run this guy. It solves very fast because I'm just doing a series solution to the differential equation. So I'm not putting this into an ODE solver, right? So I'm actually solving this directly. That's one thing that's nice about this diffusion approach. Many times in complex systems and in nonlinear dynamics, you're kind of beating things over the head with a computer using ODE solvers. In this case, it's a series solution, but it's actually exact in the sense of the series solution. So what's happening here is here's the original concentration starting out at 100% on one of the nodes, and then that's decreasing in time as that concentration diffuses into the neighboring nodes. So here are the neighboring nodes. In fact, you can almost see the degree numbers. So here's 1, 2, 3, 4, 5, 6, 7. Maybe there was an 8th in there. And so the node that was picked randomly just happened to have 7 or 8 links out. And so here are the first nearest neighbors, but then it'll diffuse out to the next nearest neighbors, and then the next nearest neighbors, and the next nearest neighbors, and then these all start to then combine. But you'll see at long time it actually asymptotes to equilibrium, so that there's all the concentrations are the same, so that the right-hand side of the diffusion equation then goes to 0. This is the fixed point of this flow. Now the fixed point is at time equals infinity, but it is an equilibrium solution. This is just looking at concentrations or log concentrations as just a function of node number. And so you start off with all the concentration on node 1 and 0 on all the others, and then you let time run, and you can see that it all actually goes out to the average of log equal to -5 in this case. All right, and so this is the ER. So let's now look at the scale free. But before we do that, let's just get a sense of sort of we'll call it the decay time, right? So it looks like this decays. Now actually it's on a log, and so it's down an order of magnitude at around, we'll call that 25. Okay, so now let's go actually to a small world with roughly the same degree, average degree. And we'll see that in fact this actually is a little bit slower, that it's going down to about an order of magnitude. That's maybe closer to about 35, and so it's a little bit slower. So the small world, it's a little slower diffusing out. Now the rewiring probability was 30%. That's actually fairly high, but it is showing that it's actually slower than the ER. And again, this is the diffusion or the concentrations on all the different nodes. Let's look at the scale free then. Again, roughly average degree is the same, around between 7 and 8. And then this actually is even faster. So this actually goes to about 1/10 concentration at about maybe 5. And so the scale free is actually much faster diffusion. And the reason for that are the hubs. And so the scale free has these very high degree hubs. And even if I picked, and I'm not sure about the degree. In fact, I guess we can actually look at that. All right, so we can try to figure out what was the degree of the first node that I picked. All right, and that's going to be given roughly by these first that come up. These are the nearest neighbors. So it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, that's definitely higher than the average degree. The average degree is about 8 for this network. And it looks like I picked a node that had a degree of about 12. So this was already somewhat of a hub. But the point is that even if it weren't a hub, within one time step or a couple time steps, I'd get to a very high degree hub. And then those have connections out to virtually the majority of the nodes that are in the network. And so the scale free, you can see that things diffuse very rapidly. The small world, it's a little counterintuitive. You think of small world as being the fact that you're only a few steps away from any member of the network, but the initial structure of having basically an M cycle, it tends to mean that you have to actually kind of diffuse a ways before you can hit one of these short circuits. And then you have to diffuse away and then hit another short circuit. So it actually does take sort of longer to get around sort of the remnant ring structure. With the 30% rewiring, there's this remnant ring structure. It takes longer than for the scale free to get around it. And then the ER is actually somewhere in the middle. It's faster than the small world, but actually slower than the scale free. And part of that has to do with the eigenvalue spectrum, right? And so we can actually look at the eigenvalues. And so here's the eigenvalue. I think the last thing I ran was, scale free. So here is the eigenvalue spectrum for the scale free. And you can see that the eigenvalues can actually get very large. And you know that the solutions are going as e to the minus beta times lambda. So if lambda is large, that's going to be fast. So let's actually look at the small world. So this looks like it's up at around 41. So let's go to the small world. Okay, and take a look at its eigenvalue spectrum. And what we see in this case is that the maximum eigenvalue in this case is actually only about 14. And so just by looking at the maximum eigenvalue, you can actually get an estimate for how fast this diffusion will go. And so the ER should be somewhere in the middle. Let's actually test that hypothesis. So we look at the ER. That was kind of intermediate time scales, and its maximum is actually just a little bit higher. It looks like it's around 16, so a little higher than for the small world, but definitely smaller than for the scale free. You'll also notice, though, that for the ER, that this is, I'm going to say, a lot flatter. The ER, there were a lot of really low eigenvalues, and then it kind of zoomed up, and then this is kind of flat. So let's go back and look at the scale free. So looking at the scale free, and we look at the eigenvalue spectrum, you see it's somewhat flat and then zooms up. So it's not just the maximum eigenvalue. It also there's a lot of eigenvalues that are fairly low, and so while it is ultimately faster, it wasn't 3 times faster than the small world, let's say. Okay, which if you just went off of the maximum here, in this case 34, it's faster than the small world, but not not by the ratio of the maximum eigenvalues, because it has to do with density of states, right? So these are all different states, and all these states down here have a fairly high density at low eigenvalue, and so those would actually be changing. Those parts of the eigenvectors would be changing slowly. So that was an exact series solution of the diffusion equation on this discrete network. We'd like to actually look at another approach, which is a matrix multiplier approach. And so this gets back to thinking in terms of the discrete models and the things like the logistic map, right? And so let's actually look at a master equation for diffusion on the network. And so this is going to take the form of a concentration on node I at time n plus 1, and then that's going to be proportional to the concentration that was on that same node at the earlier time n. And so I'll take a 1 minus, now there's going to be the amount which is leaving the node, so I'm going to call that first beta prime, and then it's going to be proportional to the number of links out. But then there's also going to be an influx, and I'll do this as beta prime, and then it's coming in from all over, and so we have the adjacency matrix, and then we also have the concentrations at time n from node j. And so that's a way of thinking of this in discrete time. So previously we were continuous in time and discrete in space, and so that was a set of coupled ODEs, and we solved them using an exact series solution. This way we're actually going discrete in time. So this really is then finite difference in both time and space. Again, it's an approximation for an ODE, but now we've made it discrete in time. But it becomes a discrete map, because now what we're doing is looking for a multiplier where we can have a concentration vector, and that would be a vector, an n-dimensional vector with the concentration values for each of the nodes. And then you just keep multiplying it by a transition matrix, okay? And again, this is a master equation approach. So first of all, let's actually identify beta prime. And so I called it beta prime because we are now actually making an approximation. I'm going to call that beta dt, or really, since it's discrete time, it's really beta delta t, but we can make our time divisions very fine if we want to be more accurate. And so this is also an approximate approach to doing the ODE solution. Well, let's try to turn this into a matrix multiplier. And so we're going to look at the concentration, which is now going to be a vector, an n-dimensional vector, but at time, capital N dimensional vector, but at time little n plus 1. And so then that's going to go as the identity matrix, and I'll actually draw it as a matrix like that. And then the outflux, so minus beta prime, I'm going to write this as diagonal. We know that those really are just Kronecker deltas. And then there's the influx, right? Beta prime times A, and then that's multiplying C sup n. And what I'll do is I'll recognize the minus D plus A as a graph Laplacian, and so then this becomes the identity matrix minus beta prime times L matrix operating on C sup n. And now we actually play the game of the map and the Floquet multiplier. What we do is we recognize that this is equal to I minus beta prime L to the n multiplying by the initial conditions. So this is an n-dimensional vector of concentration values. So it's C10, C20, C30, dot 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 to Cn0. So these are the concentrations on the n nodes, and then this becomes the Floquet multiplier. And so the Floquet multiplier, we'll just call that m. And so we just have that m is equal to the identity minus beta prime times the graph Laplacian. Okay, and this way you just have your initial concentration vector, and then you just keep multiplying that by this. It's a Floquet multiplier, but it's called a transition matrix. All right, so you keep multiplying it by this transition matrix n times to get out to the nth time step. I do want to show that we can make an approximation on this, and so that if we look at this at early times, then I can actually make this just a Taylor's expansion, so that I bar minus beta prime L bar raised to the n becomes, if I take very small time steps, this becomes roughly I minus beta prime L bar n. And n is actually just going to be related to dt, and so then this becomes just I minus beta L bar, and I'll just throw in the dt then. Okay, and so then this way we can actually recognize that Cn plus 1 is going as 1 minus beta, and I'm going to throw in lambda max. We know that that's just another approximation, but it allows us to get a sense of how fast the initial concentrations are going to be changing, and especially the initial concentration for that node that is getting the bulk of the concentration at t equals 0. And so we do see that there is actually then the same kind of relationship or dependence on lambda max that we also saw for the exact series solution. So let's take a look at how good this approximation might be. So what we're going to do is run the same programs that we did before and compare the exact discrete series solution with this approximate Floquet multiplier solution or transition matrix solution. So let's go back to the ER and we'll run this. These are just selected nodes that I picked. I did not pick the original node that had all the concentration, but you can see that the concentration is coming up on some neighboring node and then decaying away. And so here's the exact solution, and here is the continuous, or the actually, so I have them flipped. All right, so this is the continuous solution over here. This is the exact solution, and then this is the approximate solution. And you have to look pretty closely to see differences. They're pretty close. Now, part of that has to do with the fact that I picked a relatively small dt over here, so that, in fact, the discrete solution is fairly accurate compared to the exact. You'll notice that there's a little difference in when it reaches maximum time. It looks like it's reaching maximum time there at the 49th step, and this is the 46th step. That's kind of a minor difference. As I said, these are pretty close. Let's see, this crossing point here is at time step 77, and then this is at 80. Again, so it's really very close in the two solutions. That was the ER. Maybe that was easy. Let's go to the scale free, which tends to be more sensitive to these kinds of properties. And again, we see that the continuous, this is the exact over here, but then the approximate is very close to that. And so this matrix multiplier approach, and it becomes arbitrarily accurate if you let your dt take that in the limit that it goes to 0. A closely related problem to diffusion is the spread of an infection in an epidemic, and we will be doing epidemics in a later chapter, in the population dynamics chapter. But we can take a first look here and see how we're going to model that. It turns out that with epidemics, you tend to think in discrete terms of being infected or susceptible or reinfected. And so it's natural to take the matrix multiplier approach, and so we'll extend the matrix multiplier approach. But it's no longer a concentration which is diffusing. It's a condition. You're either infected or you're susceptible, and so you're looking at a discrete state, which is really a binary state. And so that just modifies the matrix multiplying equations just a little bit. So what we'll do is we'll modify those, and we'll look at the state of node I. I'm still going to write it as a C, but it means that C is either a 0 or a 1. You're either susceptible or you're infected, and then C of 1 is infected. And so we look at time step n plus 1. And so then that's going to be equal to a step function, and I'm just going to use a Heaviside, because the Heaviside is a convenient way of programming this up in MATLAB, or you could just use a ceiling function as well. So I'll use a Heaviside. And so you're taking the Heaviside of really the right-hand side of the diffusion equation. So this becomes Ci at time step n. I'm going to lump the graph Laplacian just into a stochastic function, and it'll be a function of beta prime. And this stochastic function will be either 1 or 0. So it's a binary, but it's a 1 with a probability set by beta. And then we'll still have to be governed by the connectivity of the whole network. And so I'm going to throw in the Aij, and then I'll have the concentration on node J at time step n. Okay? And so what we can do is that's what's called SI, or susceptible infected. And in this case, the infection, you never recover. And so if I have a single node that's infected, and if I have all the nodes connected, eventually they'll all be infected and they won't recover, and that's SI. So we can also have what's called an SIS model, which is susceptible, infected, susceptible, where you can recover from your infection and you become susceptible again, so you can be reinfected. And so let's look at that. We really just have to have a decay term that we have to add, so that if you're infected, you can transition back to being susceptible. And so the state of node I at n+1, it'll be this heavy side. And so then this is going to be the same thing. It's just going to be ci to the n, the stochastic function of beta prime, sum over ij, aij, cjn times up n. But then we have to subtract off. And so this is the probability that we're going to recover. And so that's going to be proportional to, or given by your state. Again, that's binary. And so if you're at 0, there's no term here. If you're 1, then you're actually going to be losing your infection, again, with this stochastic function that's 1 or 0, binary. But it'll have a new rate here. So this is the recovery rate, mu prime. So there's an infection rate, beta prime, but a recovery rate, mu prime. And so then this would be called the SIS model. And this, in a way, is more interesting because now you can actually watch the infection spread out, but then people recover. And then it comes down to things like the average degree as to whether this infection will persist or possibly die out. And it can die out if the connectivity is low enough and the infection rate is high enough and the recovery rate is, infection rate is low enough, recovery rate's high enough, and if the connectivity is low enough, then in fact you can have an epidemic that can die out. And so this becomes a discrete way of modeling this in a network model, and so then we'll look at the MATLAB again. So this is now an SIRS model. In this case, this can be removed where we can talk in terms of inoculation, but we can do that as homework problems. For this case, we're just going to look at what happens to ER graphs, SW and SF graphs when we start out with a single infected node, and then we just let that run and we run our discrete model on that. So let's actually start with the ER. And what you'll see is the network is represented in a circle, and one of the nodes will start out infected, and then on each time step there's a probability that it'll infect its neighbors, but then they can recover. So this is an SIS. So what we're going to look at right now is an SIS model. And so there we have the infection is in red, and you can see that it goes pretty fast. And so we probably did not see the original infection. There was just a single infected node. And so then as this runs in time, you get recovery so that you become susceptible again, and so you can become infected again. This is then the total number of infected nodes as a function of time. It got as high as 16, went out 100 time steps. Looks like the average here is about 8. The total number of nodes was about 50 in this case. Let's actually run it again. I'm looking for a certain behavior. So here it is. Okay, we're running, and the infection is persisting. Not very prevalent, though. There aren't that many nodes that get infected. And we let this run in time. And I'm not seeing what I'm looking for. Figures, the last time I ran this, it happened right away. Let's try it one more time. And so here we go. And it's not going to cooperate. Oh yes, it did. Okay. So this is the total number of infected nodes. And so what you'll see is that it went to 0. So the infection died out. And at some point it was as high as 19 nodes out of 50 were infected. But not too long after that, it actually died out. And so this is where you can have, because it's discrete, one of the fixed points in this discrete map is to have the infection die out. There's a finite probability. Anytime you have a discrete infection model like this, there's a finite probability that it just goes away, that you get down to a single infected individual, and that individual recovers before they can infect their neighbors. Let's go to actually a scale free, since we know that that's kind of an extreme behavior because of the high degree hubs, and we'll take a look at this. And so here we have the infection. I can't say it's diffusing. This is a diffusion model, but it's jumping around. In this case, also, it looked like, in fact, it doesn't look like, it did die out, and so it died out at around 55. Let's just run it again, see where it dies out. And you can see these high degree nodes over here, right? You can see all the links coming out. All right, so this infection is kind of persisting. It looks like a little bit longer. Quite a few reds in there. Yes, and so that, in this case, did not die out. But there's always a finite chance that it'll die out. You let this run long enough, and it might die out. Again, there were 50 total nodes. It looks like our infection is running at around, let's call that 12 out of 50, or about a quarter of the nodes are infected in this case. Just for completeness, let's go over to the small world and take a look. These all have roughly the same mean degree. You see the short circuits there, and so the M cycle is very well preserved in this case. It looks like I actually only had an M of 2. But in this case, we're getting a fairly strong infection. It could just be an accident of this Monte Carlo. You do see that it definitely was growing in time, also averaging out to about 12. The 12 comes from a balance between the infection rate and the recovery rate. So if I change my betas and my mu's, I can change the average number of nodes that are infected. Let me make this an M cycle of 4. Let's see what happens here. That's a little bit more like a small world. I'm not sure we're going to see any significant difference from the last one, but we'll take a look. And you have to run lots of these. This is called, we're in Monte Carlo mode. You would run 100 of these or 1,000 of these simulations and take averages. And there'd be an average time to having an infection die out. There'd be an average rates at which the network becomes infected. And so you can then get statistics on the average properties. So this actually looks quite different, right? So this actually came up as I changed, because the M went from 2 to 4. We definitely boosted the average number, and so in this case, obviously, the average infection on the network is a function of how many of those links you have to nearest neighbors. Okay, and so anyway, so this then becomes a way of doing numerical experiments. You can form a hypothesis that something should or should not depend on M, and you can run Monte Carlo and get good averages, and you can test these hypotheses. And then that just opens this up. You can actually do some pretty nice studies, actually, looking for different dependencies between the different network architectures and how this infection will diffuse around and recover. You can also bring in an R, which means removed. You can make people immune. Either they have natural immunity, or possibly you inoculate them, and you can actually turn on an inoculation in this case. And so this program, this MATLAB program, is on the GitHub account associated with this course. And so you can actually go and find this SIRS at my GitHub.